The Kashiwazaki-Kariwa nuclear power station operates 7 active units, producing a combined capacity of 8.212 gigawatts. The complex physically spans across Kashiwazaki City and Kariwa Village, situated directly on the coast of the Sea of Japan in Niigata Prefecture. That multi-gigawatt output ranks it among the absolute largest nuclear power stations on Earth by installed capacity. For its operator, TEPCO, it serves as a critical node in Japan's power infrastructure, capable of injecting vast amounts of carbon-free electricity into the national grid. Building a power center of this scale demands massive industrial architecture, but placing it on a seismically active coastline creates a severe structural engineering paradox. On July 16, 2007, a violent tectonic rupture fractured upward through the bedrock beneath that exact coastline. The Niigata Chuetsu-Oki Earthquake collapsed local infrastructure and leveled residential zones with sustained heavy ground motion. The Kashiwazaki-Kariwa facility absorbed a direct hit from those extreme seismic waves. Measured, deliberate, the physical tectonic forces unleashed that day significantly surpassed the theoretical design thresholds the plant was built to withstand. Surviving an event that exceeded its own engineering parameters turned the facility into a vital real-world case study for nuclear seismic behavior. This wireframe illustrates a nuclear station cycle. Fission generates heat, boils water, and steam drives a turbine. This is a boiling water reactor. Water boils directly in the primary system. Looking at the layout, Units 1 through 5 operate on this standard architecture. The remaining units utilize the successor technology, the advanced boiling water reactor. This modern iteration improves upon the older design by integrating upgraded internal safety systems and optimizing the overall physical plant layout. TEPCO deployed this advanced design specifically for Units 6 and 7. The site combines older legacy reactors with modern automated systems, all of which must hold together as a single structural unit when the Earth moves. When the 2007 earthquake struck, kinetic shock waves from the shifting bedrock slammed directly into the plant's rigid concrete foundation. This graph plots ground acceleration over time. The dashed horizontal line represents the maximum design basis threshold. The jagged line tracks the actual recorded ground motion, surging sharply above the threshold. The red area defines the severe gap between mathematical models and physical forces. Pushing a multi-gigawatt facility past its calculated safety margins places extreme mechanical stress on every concrete column and steel weld across the site. Because the facility was built with massive inherent design margins, the central reactor vessels themselves did not breach. However, the peripheral mechanical systems located outside the core absorbed severe damaging loads. True seismic resilience is measured across the entire facility footprint. The safety of the reactor core remains contingent on the integrity of every peripheral pipe and anchorage point. This cross-section highlights soil-structure interaction. As seismic waves traveled horizontally through the Niigata coastline, varying soil densities altered their speed and wavelength. The momentarily liquefying soil applied massive, uneven differential pressure against the unyielding perimeter of the concrete foundation. This varied ground compaction leads to differential settlement, where one section of a heavy structure sinks slightly faster than another, warping the architecture above. A multi-gigawatt nuclear facility's structural integrity is dictated by the mechanical response of the soil layers as much as the steel used in its construction. Following the quake, the International Atomic Energy Agency conducted a comprehensive structural review of the site. Their objective was to extract actionable engineering data from a facility that had successfully absorbed forces beyond its assumed limits. The review isolated severe vulnerabilities in the rigid piping systems, which faced intense bending and shear forces. Heavy equipment anchorage was equally stressed. Massive steel bolts securing generators to the floor bore the brutal brunt of the ground motion. Beyond the hardware, plant operators faced the severe logistical challenge of executing complex emergency response protocols while the floors were actively heaving beneath them. The event exposed the inherent danger of relying purely on static mathematical predictions when actual tectonic variables are chaotic. The IAEA's findings pushed structural engineers globally to rethink secondary piping and equipment anchors. A reinforced reactor core remains safe only if its supporting components stay attached to the floor. 4 years later, an entirely separate tectonic event on the opposite coast devastated the Fukushima Daiichi plant. The fallout from that disaster forced an uncompromising revision of the safety standards for every nuclear facility in Japan. The government mandated a nationwide suspension of nuclear operations, placing all existing plants under a rigorous state of safety review. Concurrently, public sentiment hardened, generating intense national and municipal resistance against proposals to restart offline reactors. Surviving a massive earthquake was no longer the sole metric for safe operation. A facility now had to demonstrate resilience against compounded natural disasters while navigating absolute public scrutiny. To enforce these exactingly high standards, Japan established the Nuclear Regulation Authority, a strict governing body tasked with overseeing the post-2011 infrastructure. According to official NRA logs published in early 2026, the operational status of the Kashiwazaki-Kariwa units remains suspended, pending periodic operator inspection. The technical safety metrics demanded for a restart now vastly exceed the initial structural upgrades implemented after the 2007 earthquake. Furthermore, the regulatory debate has expanded beyond physical engineering. TEPCO must continuously prove flawless internal security management and operator reliability. Any path forward requires securing complex municipal consent while keeping the plant's output aligned with Japan's broader national energy strategy. All the while, 8.2 gigawatts of carbon-free generation capacity sits idle on the Niigata coast. Kashiwazaki-Kariwa stands as a massive monument to modern structural engineering, proven capable of withstanding extreme tectonic violence, yet ultimately immobilized by the zero-tolerance reality of post-Fukushima regulation.